Okay, hello. Let's start the class now. So we will talk about exam 3 solution today. Okay, let me double check. Okay, so question 1 asks, suppose that we are looking at this algebraic system with q plus the positive rational numbers as our set, and then multiplication, the standard number multiplication as our operator. We want to find out whether this algebraic system is a group or not. And the answer is yes. And in order to show that it is a group, we want to show 4 things. We want to show that this operator, this binary operator, is closed. And then we want to show that this binary operator is associative. We want to show that there exists a identity element here in this Q plus. And then we also want to show that for every element in Q plus, there is always an inverse, such that applying the operator on the element and its inverse, we will get the identity. So this is a standard procedure. So to show that it is closed, it's easy. So suppose that we have any two elements xy selected from this set. So because it is a positive rational number set, so x can be expressed as the ratio of two positive integers, and similarly y is also a ratio of two positive integers. So we can assume a, b, c, d here, they are all positive integers. Now when we apply this multiplication on xy, we will have x times y is equal to this one times this one, and then this is from the multiplication of rational numbers. We will see that it is ac divided by the product of bd. This is an integer, this is an integer, this is positive, this is positive. So we will see that this is also in Q plus. In that case, we have shown that the operator multiply is a closed operation. And similarly, we can show that this multiplication is also an associative operator. So this time we assume we are looking at x, y, z, not necessarily distinct, so they can be any elements in Q plus. So x can be written as a over b, y, c over d, z, e over f. Then, to show that it is associative, we compare the result of, we first perform x times y first, and then multiply with z, or we perform y multiply with z together first, and then have x multiply with the product of here. But in any case, we will see that these two are exactly the same. Okay, so they are all the same as ACE divided by BDF. So we will see that they are all the same. So in that case, multiplication is an associative operator, has associative property. Identity is easy. 1 is an identity item, and then because any element x multiplied with 1 is equal to x, and any element 1 x such that 1 multiplied with x is also equal to x, so it is an identity element. And then for each element x, let's say it is equal to a over b, we will see that the element y, which is equal to b over a, is also a positive rational number. And then if we multiply these two together, we will get 1. So every element has an inverse. So that's for Q1. So Q1 should be very easy. Just test your understanding of what are the properties of a group that we need to have. The second one is we want to find out what is the last two digits of 53 to the power 723. And then for this question, we actually can find this out without using a calculator. Now the answer for this one is 77. Now to get the last two digits, it is the same as we want to make this number divide this by 100 and find out the remainder. Okay, so we want to do a modulo by 100 operation. There are many ways to do so, so this is one way that I chose. Okay, so first of all, we see that 53 is co-prime with 100. So we are going to apply the Fermat-Little theorem to help us. Oh, not Fermat, but Euler. Yeah, it should be the generalized Fermat-Little theorem. So the Euler's theorem. So in order to do that, we are going to find out what is the value of 53 to the power 723 modulo 100. Now to simplify this, we first find out what is the phi value of 100, and it is simple, it is equal to 40. So when we want to compute 53 to the power 723 mod 100, we can take away as many 40s from the power as we want, because 53 to the power 40 is equal to 1 modulo 100. So by taking a lot of 40s, we will see that this one is what we want to find out, but it is exactly the same as 53 to the power 3. Now 53 to the power 3 is equal to 50 plus 3 altogether to the power 3. So by using the binomial theorem, so this binomial theorem, 53 to the power 3 is equal to this one plus this one plus this one and this one. Now we see that this is a multiple of 100 because I have 50 multiplied with some even number. So it's going to be 0 when we divide this by 100. This is also a multiple of 100 because we have 50 times 50. So 50 times 2 here already. So it is also 0. This one is an odd number, 27, right? Times 50. So we take away all the even numbers times 50. So we get 50 left. Because all the even numbers times 50, we will get a multiple of 100. So this is equal to 50 modulo 100. And 3 to the power 3 is 27. So 50 plus 27 is 77. Okay, so this is the second question. The third one is we have an RSA system, and then it is given the public key 101 and 779. So this is the E part, and this is the N part. We want to find out what is the private key. So the private key will be DN, right? So the value of D will be 221. So we require that we require you to find this private key by using the extended Euclidean algorithm. So let's run it together. Now before we find the private key, we have to first find out what are the prime numbers what are the prime factors of 779, because this is important in getting the private key. So we find out that 779 is equal to 19 times 41. So phi of n is equal to 18 times 40, which is 720. And the private key that we are trying to find will be an inverse of 101 modulo 720. So this is what we want. So in that case, to find out the inverse of 101 mod 720, we apply the Euclidean algorithm on 101 and 720. Okay, 101, 720. So let's express 101 as 0 times 720 plus 1 times 101. So as for 720, we express this as 1 times 720 plus 0 times 101. Okay, so in such a case, then 101, we deduct as many multiple of 101 as possible from 720. So this is going to be 0, 7, because 7 times of this one is 0, 7, right? The resultant will be 1, 3. 1, 3 comes from 1 minus 0 is 1, 0 minus 7 is minus 7. 19 is 7 times of this value. 91 is 7 times of this value. So the bracket here is 7 minus 49. So we do this again and again. We will find out that 1, the value of 1, can be expressed as minus 31 times 720 plus 221 times 101. And in such a case, we find out that the inverse of 101 is this number, 221. Now, once we have this 221, then we can apply, this time you can use a calculator, you can use you can write a program and then decrypt the message that we have. And then, yeah, after decryption, if it is successful, then you should get this as our encrypted message. Okay, so this is question number 3. Question number 4, we are coloring a regular hexagon. Now, the vertex of the hexagon can be colored either in black or in white. And each edge, it can be colored in red, green, or blue. Now, two colorings are the same if one can be obtained from the other by rotation. So we assume that the polygon, the hexagon, is rotating on the plane only. So we are not doing any flipping. And then we want to find out how many distinct colorings. Okay, So here, this is a standard Burnside theorem question. So we let S to be the set of all colorings of the hexagon, and then a permutation group G dot is formed, where this permutation group will have each permutation. So this permutation group will contain a lot of permutation, and for each permutation, it corresponds to a mapping of S to S due to a series of rotations. Now this G will now have exactly 6 elements corresponding to the 6 different types of rotation that we can have. So Burnside tries to find out how many fixed points in each case. Now for this question, we can actually combine the view of an edge with a neighboring vertex. Let's say the vertex that is attaching to the edge in the clockwise order together as a big object. So we will see that there are 2 ways to color an edge and 3 ways to color there are 2 ways to color a vertex and 3 ways to color an edge. So that means that there are actually 6 ways to color this big object. So in that case, to calculate the number of fixed points, we will see how this will come. Now, the number of different coloring will be 6 to the power 6, because each big component of edge vertex case, there are 6 ways to do so, and there are 6 groups, so 6 to the power 6. But if you want to make it the same even after rotation by 60 degrees, then there are only 6 different ways. Now by computing this one by one, you can find out the fixed points in each of the permutations. So there are 6 ways, 6 permutations. We add them up, compute the average. So this is the Burnside theorem. So the number of distinct colorings will be the average of these values. So it is 7826. Is it? Yeah, if my calculation is correct, something like this. Yes? Okay, finally, we have question 5. So we let P to be a prime greater than 2. So we want to ask you, can we compute the value of the Catalan number P modulo P? And the answer here is a really simple number. It is always equal to 2. Now, actually, this is also true when P is a prime equal to 2. So even it is true it is equal to 2. So the answer will be 2, even P is equal to 2. But then we are asking about the remainder. So 2 divided by 2, the remainder will be 0. So this is a different and slightly different case. So for all the other primes, the remainder will be 2. So how do we show this is correct? So we need to have this general lemma to help us. So we claim that, so this is what we want to find out. Suppose that x is a number that is co-prime with p. So p is a prime, so that means that x is not divisible by p. And x divides a properly. Then we will have this one, a divided by x will be an integer. And then if we multiply this by x, then we will see that, so this is a over x multiplied by x, so integer multiplication, so x and x can cancel, so it must be equal to a. This is always true, but then what we want to claim here is that, suppose that we multiply x inverse on the right hand side of these two numbers, then we will see that this number multiplied with x inverse will be equal to a times x inverse. Now when x is co-prime with p, this is well defined, so we can have something like this. And then when these two are multiplied together, this is equal to 1 modulo p. So actually, we want to claim that a over x, you can express it as a times the inverse of x when we are talking about the modulo p operation. So now, this is a Catalan number Cp. This is what we can write down for 2p choose p. So we can write it down as there are 2p, starting from 2p, there are p numbers decreasing, multiplied together, divided by p factorial. So this is the same as 2p choose p. Now, we are talking about modulo p operation. So 1 over p plus 1, we can replace it by p plus 1 to the inverse of p plus 1. So we keep this unchanged, except that we have 2p divided by p. We can take it out. 2p divided by p is 2. So it is an integer value, so we can just simply take it by 2. This is the remaining part. P plus 1 inverse is equal to plus 1's inverse. So because p plus 1 and 1 are the same number, modulo p. So this is actually 1. This part is 1. This is 2. This is 2p minus 1, 2p minus 2 up to p plus 1. I copy this. And then we have this one. Let's have this one's inverse. Is that okay? But then 2p minus 1 is the same as p minus 1 modulo p. This is the same as p minus 2 modulo p, and so on and so forth. So this is equal to 1 modulo p. So the product of this one is exactly p minus 1 factorial. And then when it is multiplied with the inverse of p minus 1 factorial, these two cancels with each other. So these two becomes 1. And so the value will be equal to 2 modulo p. Okay, yeah, so that's all for what we want to show. So this is let me see. So this is exam 3. Yeah, okay. Yeah, I hope you find this exam not that difficult. So probably question number 5 is requires some thinking. But in general, I hope that you like this exam. So thanks all. And then this is going to be the last YouTube live for this course in this semester. Yeah, thanks for joining. And then see you again later. Okay, bye-bye.